Now, so today we are going to have a look at the atomic packing factor of a body-centered cubic structure. In a body-centered cubic structure, the atom is cubic because a body-centered cubic. There are 8 corners of a cube, and these atoms at the corner atoms are, so these are corner atoms. These corner atoms are there. These corner atoms are shared by 7 other cubes, including this one. So 1/8 of this corner atom is being shared by this cube. But then we got this center atom. This center atom totally belongs to this unit cell. So as you can see, that center atom totally belongs to this unit cell, and this is 1/8 of a sphere. So this is the body center cubic structure. If we want to find out the total number of atoms required for the unit cell of a body center cubic, we do corner atoms. Now the corner atoms, there are 8 corner atoms, and 1/8 belongs to that one. So if I add all the corner atoms, I will have 1 sphere. Center atoms is just 1 center atom, and all of that belongs to that unit cell. So the total number of atoms required to form the unit cell of a body center cubic is 2. So we need 2 atoms to form the unit cell. Now let's come back to the atomic packing factor. The atomic packing factor has a formula. Atomic packing factor. It's volume of unit cell volume of atom in our unit cell. Okay, now if I redraw the unit cell on this side, so let's imagine we got a unit cell, a cubic unit cell. Where A is the dimension of this cube. So if I want to find out the volume of this cube, I have one length, the volume of the cube, the volume of the unit cell is a cube. So we have the volume of the unit cell as a cube. Now we have to make an assumption. Our assumptions are unit cells, all the atoms are non-compressed. You can't compress the atoms. They act like a solid spheres. Now, if I draw a unit cell of a simple cubic structure or body-centered cubic structure, you can see here this length from here to here, it's a A. This length from here to here, it's a A. I want to find that length. But if I want to find the length from all the way from here to here, that will be different, like cross diagonal. From that point to that point, cross diagonal, or this length from here to here. Yeah, I want to find the diagonal length. That will be different. So let's figure this one out. So let's have a look at that bit. Let me draw the cube. It's not going to be perfect cube, but Now you got an atom here, and you got an atom here. You got another atom here. Okay, and you got another atom here, which is, yeah, that's supposed to be on both sides. Let me redraw it. Okay. I'm trying to find out this length from here to here. That's the length. I know this length is an A, and I know this length is an A as well, because it's a cube. So if I draw a triangle, where this is an A and this is an A, I can find the hypotenuse. So let's find the hypotenuse. Hypotenuse, we have a Pythagoras theorem. Hypotenuse square is equal to that square plus that square. So A square plus another A square. Now A square plus A square is going to be 2A square. So that's the length of this hypotenuse. Rather calling it a uppercase H, I use a lowercase h for the hypotenuse. H square. That's the hypotenuse square. So I got this hypotenuse square. Now I need to find out the big hypotenuse. The big hypotenuse is from this corner all the way to this corner. That's the big hypotenuse I'm trying to find out. There is a theorem which says all the diagonals in a cube is same. What I mean by that? If I measure that diagonal from here to here, this is same as the diagonal from here to here or here to here. All the diagonals in a cube, they are same. But the diagonal in the cube, which is the big diagonal from here to here, this is the biggest diagonal. Yeah, it's from that corner to all the way that corner. It's called the body diagonal, not the face diagonal. Face diagonal is the same on just one face. The body has to go through all the body. Now, if you have a look here, I want to start from this point, and I want to end at the point on the side. So it has to go through this atom and then the bigger body center atom, and it will end on the other side. And this is the diagonal I am trying to find out from here all the way here. Now, when I look at the crystal structure of that one, the distance from here to just here, that distance is just one atom, one radius, because they're all the same atom. So from here to here is one radius, and then here to here is one radius. So this big diagonal is the length of 4 radius. How come 4 radius? Because then there is a big atom in the center. That is distance from here to here is 2 radius. Okay. So if I redraw this bit in an exaggerated form, this is 1, and then this is start from, this is the other bit, which is that side, another one, and then there is another one. So this is an R, this is an R, and this middle one is another 2R. So the total length of a diagonal, a body diagonal, is 2R. I call this body diagonal as uppercase H. Did I say 2R? 4R, sorry. Why 4R? Because R plus a 2 radius plus another radius. So that's a big diagonal. The body diagonal is 4R. So now we got the body diagonal. Now I have the body diagonal. Now I'm just going to redraw this one now. Let's say we got a cube now. And I want from one corner to another corner. I have the big diagonal from this corner to that corner. That's a big diagonal I got. I know this value. I already know this value because this is the A. But what about this value? This is the face diagonal. I already calculated this face diagonal. What's the value of this face diagonal? If you have a look, H equals, if I square root both sides, and that will become square root of A, not square root of A, square root of 2 and square root of A squared, which if I simplify, it will become root 2 and that cancels A. This is the phase diagonal. I have the phase diagonal. So if I redraw this one, if I redraw that one, that is going to be another right angle triangle. So let me redraw that one on the top. This is a black line. This black line here. This length is A. So we have that one. This black line, I'm just going to use red color. This is that length. Yeah, which is 4R. And this blue line is that line. Now, what is this blue line? This blue line is the diagonal, phase diagonal, root 2A. So I have that bit. Now I'm just going to clear the screen. Let's clear the screen. Okay. Now I want to find out the 4R. This is hypotenuse. So I'm going to use a Pythagoras theorem, which says hypotenuse square equals to the adjacent square plus the opposite square. Adjacent is, I can use that one. Let me use the black color. If I square that one, root 2 square is just a 2, and that's an A plus an A square. If I simplify that one, that will be 3A square. 3A square is the big hypotenuse. So I call that one big hypotenuse square. But I want a big H. So I square root both sides. So that will be H. And when I square that one, that will be 3. And when I square this one, this is going to be that. If I simplify this bit, that's what we got. Now remember, what's the H? H was 4R. So instead of this H, I can put the 4R. So let's put the 4R there. If I put the 4R here and 4R here, so that becomes a 4R squared. That will give you 16 R squared. Yep, so that gives you 16 R squared. Now I need to move the 16 on the other side. Just want to find out the R. So in that case, what I can do is, if I just clear that bit and clear that bit, I'm just going to do R. R square is 3A square over 16. Now I need to square root both sides. I need to square root this side and I need to square this side. So that side is just going to be R. This side is going to be root 3. Square root of 16 is just a 4 and square root of A square is just an A. So this is the relation between R and A. When we got this relation between R and A, we keep that one. Next thing we need to know is, let me just clear this bit. And if I write that one, the R equals root 3 over 4A. So I have this bit. Now, and yeah, I just find the smaller R there. So we don't need this one now. So I'm just going to clear that one and clear that one. Now we just go back to the formula, atomic packing factor formula. So we have atomic packing factor. The volume of the unit cell, because the unit cell was A times A times A. Volume of the unit cell is just going to be A cube. Volume of the atom in the unit cell. Volume of the atom, because the atoms are sphere. So volume of the sphere is, that's the formula. 4/3 pi r cube. But this is one sphere. Now, because we said there are 2 atoms are required to form the unit cell of a body center cubic, hence there is a number 2 because there are 2 of them. I can simplify this bit, and I can say that one 2 times 4 is 8, so that becomes the 8/3 pi r cube over the a cube. Now I will go back to my formula, which is here, and I know what r is. The r is √3/4a. So instead of r, I'm just going to put that value. So I got 8/3 already. Pi is there already. Instead of r, I'm going to put √3/4 a cube over this a cube. Now, when I got that bit, when I got this bit, now I need to simplify that one. 8/3 as it is. Pi is as it is. When I cube that one, √3 cube is √3 times √3 times √3. If you simplify, that will be 3√3. Yeah, if you put that in calculator, that's the answer you get. So I can call that one as 3√3. 4. When I cube the 4, it's going to be 4 times 4 times 4, which is 64. So that will be, I need to write down 64 underneath. Yeah. Okay. Then I got this a. So a is going to be the a cube divided by this a cube there. So now I can do some cancellations. This a cube and this a cube, they cancel out. So they cancel out. Now I got the other bits left. So what I can do is this 64 and this a, that can cancel out. This 3 and this 3 can cancel out. 8 times 1 is 8, and 8 times 8 is 64. So I got. So what I do is I have the answer pi √3/a. So the atomic packing factor for body center cubic is pi √3/a. If you put that in your calculator, you will get the answer as anyone 0.62. Six eight. 0.68. So which means 68% of space is occupied. And then the rest space is, yeah, so that's going to be 20, no, not 20. 32% of the space is free space. What does that mean? That means this is a lot of space that's available. The best atomic packing factor is, well, as we did yesterday, last time we did the body's face center cubic. Face center cubic has 74%. This has 68%. So if you want to pack something, yeah, if the atomic packing factor, if you want to get more density then, or more density pack, go for the face center cubic, which means the face center cubic elements will have a higher density as compared to that one, which also means they have less space available to add other elements in it.